Okay, here I'm going to talk about the optimal number of wells you may need uh, to plan for in your project, especially if you're in an early phase development project. You're planning to develop a new field, or you're evaluating the potential of a new business development opportunity. Uh, when you work in a team, this is typically something lots of people want to know as early as possible. How many wells are we going to need? The economist will ask you that question. The drilling engineer will ask you that question. Management will ask you. So even before you've had a chance to do any simulation, I'm going to explain a simple but very efficient or effective method of doing the calculations and coming up with a very good estimate. And the method is based on maximizing the net present value uh, as a function uh, of the number of wells you use. And we're going to assume exponential decline. That's one of the simplest assumptions we make. Uh, but based on that, based on the NPV as a function of the number of wells, we're going to find when or at what number of wells will the net present value peak? When will it reach its maximum? And we'll find that by differentiation. So let's start with exponential decline. Uh, the first equation here shows that the flow rate as some initial flow rate times a constant, and it declines over time. As time increases, this becomes smaller and smaller. So as a function of time, the flow rate, the production from a well, is exponential. That's the assumption. Uh, by integrating this equation, you find the cumulative production as a function of the initial flow rate and the current flow rate divided by the logarithm of that constant. So based on this equation, you can actually express the flow rate as a linear function of the cumulative production, in which case it's linear. So it's both exponential versus time, but then it's linear versus the cum. And you can even go one step further and express it as a function of the ultimate recovery, which is the cum when the flow rate has decreased to zero, in which case the flow rate is given here. And we'll be using this one uh, as we derive the equations. But remember that it is exponential decline versus time. Over time it is. So over time, the flow rate declines like this exponentially. But when you plot the same thing versus the cumulative production, you get a straight line. And at the bottom here, that's where the cum becomes or reaches the ultimate recovery. Now, in real life, there is a transient period. Uh, if you see, uh, here's a straight line of a simulation uh, where you have the flow rate versus cum. But you can see the early time there's actually uh, a transient period. Now we're going to ignore that part and just say that that is the initial flow rate of the well, the extrapolation of the straight uh, part of the curve. So that's the definition of the initial well potential. And we also assume that the reservoir is connected. It's not compartmentalized. So in theory, if you have one well, uh, that well should be able, in theory, to produce the entire ultimate recovery. It will take a long time, but in theory it can be done. With two wells in this plot, uh, you won't produce more. You'll just produce it at a higher rate and faster. And with three wells, the yellow curve here, 4, 5, the more wells, the faster you'll reach the ultimate recovery. Now, if you have a plateau rate here, capacity limit on your facility, on your production facilities, you may not want to drill all the wells on day one because you can't really utilize the total well production because you're limited. And you can see in this simple sketch illustration, I've assumed you got 1, 2, 3 wells here. I had started out with 3 wells, but as production declined at some point, I reached the plateau rate and I need to drill a new well to stay above the plateau. And then I decline again, and again I have to drill a 5th well, etc. until I reach the total number of wells I want, in which case I just follow the decline down to the ultimate recovery. Now there's a simple formula here uh, shown to the left that shows how many wells as a function of time we need to maintain plateau rate, at least the plateau rate. It's given here. And the time derivative, the change in number of wells, the speed at which you have to drill wells is given by the time derivative of this expression. So I'm going to use this formula in the NPV calculations. And now we need just one more thing before we can get to the NPV. We need to know what is the length of the plateau in time as a function of the number of wells. And again, we start with the same equation as we had here and just solve it for time plateau length. And you can see this is a function of the number of wells, the n sub w. Here's the total decline when we have all n sub w wells drilled. It just shows that the total field rate after you go off the plateau rate, when you start the decline, the field rate declines according to this formula. So the total NPV consists of the oil price times the production on your plateau when the flow rate is constant, and discounted by a factor R, if R is whatever your NPV discount rate is, 5%, 10%, 15%, whatever. And you have to integrate this from 0 to the length of the plateau, which is a function of the number of wells, remember. And then after you drop off the plateau rate, when you're on decline, you integrate from the end of the plateau to the end of the field, in which case you use this rate, which is a function of both the number of wells and time. also discounted. Here is the initial well cost and the well OPEX, the operating costs associated with the wells, discounted with the same NPV discount. That term includes all the net present value of the future operation costs per well, and that's the cost of drilling and completing the wells. And for the initial wells to just to reach plateau, and these are the wells you need to drill to maintain plateau until the end of the plateau period. And of course you have the cost of the facilities themselves, which are constant, or they are not dependent on the number of wells. So when you differentiate this term, as shown here, you want to equate this to 0 to find the number of wells that maximize your NPV. Now, all of this part of the equation is always positive. So it will never be 0. This part is never 0, and that part is also positive. The only part that will become 0 is this within the parenthesis here, the square brackets. So we need to solve this equation. That expression must be 0, but we can simplify. That part must equal this part, in which case their difference is 0. And you can see that the term here, the ultimate recovery times the logarithm divided by the initial rate, it repeats itself. It's both there and there. And then we have another term over here that contains oil price and the well cost. So if I call this A, then that of course is also A, and this is B. So the equation is fairly simple. You can see it here. It's a cubic equation in the number of wells. I just want to mention that the plateau rate and the field rate and the initial well rates, they are all standard barrels per year, because the NPV discount rate is typically a rate per year, and you need the same time unit in order to do that. So as long as you make sure that the rates are barrels per year or cubic meters per year. If you have daily rates, then just multiply by 365. But okay, here's the secret to the solution. And here's the plot that shows how to get it. You calculate A, which is the ultimate recovery, based on your estimate of the strength of the various recovery methods. Whether if it's water injection, you have a recovery factor. You have to estimate this and the initial well rates. You calculate this number, and you calculate the plateau rate and the oil price and the well costs, and you get a number here. So you mark wherever you end up here. You mark make a mark here, and whatever number you calculate here, you mark it there, and you find where they intersect. And now let's say it's here. Then that blue curve is the 16 wells curve in this case. Based on this chart, you can just go in there and do some very simple calculations and find out how many wells you're going to need. I want to point out two areas here on this chart. Here you see all the lines are parallel. The number of wells is the cubic root of a squared times b in this area. Over here they are also parallel and linear. And here the number of wells is simply the number b you get there. So when the ultimate recovery is very large, when you're over in this area, the number of wells is determined only by the plateau rate and the oil price, etc. Or if the individual well rates are low, you're also over in this area. Uh, the number of wells will simply be B. If the ultimate recovery is very low or the well rates are very high, you're in this region. Most often, of course, you'll be in between, in which case you can use this if you don't want to just visually pick out your number, you can use this iteration formula to get a numerical value.